All right, so in this video, I'm going to be teaching you how to solve logarithmic differentiation. All right, there is a technique used to solve problems in calculus which we call logarithmic differentiation. It is one of the techniques we can use to solve problems under differentiation. Now, when do we use logarithmic differentiation? We use logarithmic differentiation when we have these three cases are the cases of when we use logarithmic differentiation. Okay, case one, we use logarithmic differentiation when we have complicated products. What are complicated products? Complicated products, an example of complicated product is given here: y equal to exponential 2x sine x cos x. Why is this a complicated product? Because initially you were taught product rule, and product rule of differentiation is always used when you have two different functions multiplying each other. Now these are three different functions multiplying each other: exponential function and two logarithmic functions, sine and cos. It is complicated because you would not know which one to call u and which one to call v. So cases like this, we use logarithmic differentiation. Case two, when we have complicated quotients, something like this: 2x squared cos x over cos. Cos 2x is an hyperbolic function, all right, minus exponential x. Cases like these are complicated quotients. It is complicated because the denominator is not a single term, it is a multiple term separated by a difference in between, cos 2x minus exponential x. All right. Case 3, and this is the most commonly asked cases in logarithmic differentiation: when a variable or an expression is raised to another function or another variable. When a variable, say x, or an expression, say x plus 1, is raised to another function or variable, e.g., y equal to x raised to the power of x. This is a case where we use logarithmic differentiation. And I know you might have come across questions like this in some materials. Differentiate y equal to x raised to the power of x. Another case, x raised to the power of sine x. It can be x raised to the power of anything. So long as it is a variable raised to a function, we use logarithmic differentiation. Another case is when we have y equal to x plus 1 to the power of x, etc. Cases like this, from case 1 to 3, these are cases where we use logarithmic differentiation. Okay, now let's look at the steps. There are steps to doing this. There are steps to using the logarithmic differentiation. Now these are the steps. Step 1, let y be equal to your function. Any function you are given as a question, replace that function with y. All right, that's step 1. After doing that, you will take the natural log of both sides. Taking the natural log of both sides means you take the ln of both sides and apply the law of logarithm. Okay? What are the laws of logarithm? I will state them as we go further in this video. The laws of logarithm, or better still, I can do that here. The laws of logarithm. We have the product law of logarithm, which is the multiplication law. It states that the multiplication or the product law of logarithm states that when you have two different expressions multiplying each other under the log sign, they can be splitted in this manner: log A plus log B. This is the product of the multiplication law of logarithm. Rule 2. Log A over B, which is the quotient rule of logarithm. It states that when you have two different expressions dividing each other under the logarithm sign, under the log sign, you can split them log A minus log B. Then finally, the power law of logarithm. As we go further in this video, I'll be making use of these three laws to solve problems under logarithmic differentiation. The last or the third law of logarithm is the power law, where you have the log of an expression raised to a certain power. This states that the power comes behind n log A. Use the power to multiply the log. These are the three laws of logarithm. So these laws of logarithm will take effect from step 2. Remember, step 2 says take the natural log of both sides, ln, and apply the law of logarithm. Now, step 3, differentiate both sides of the equation, your normal differentiation. Step 4, multiply both sides by y. And finally, take back y to what it initially was. All right, so we're going to be solving some examples here and see how that applies. All right, we have some examples here. Differentiate the following functions. Y equal to x to the power of x. Y equal to x raised to the power of x. Number 2, y equal to x raised to the power of sine x. And number 3, y equal to 2x plus 1 all raised to the power of x. Let's start with the first. Y equal to x to the power of x. Now, initially, the step 1 says make the function to be y. We already have that directly here from the question. It was stated that y is equal to the variable, the function x raised to the power of x. So step 1 is already indicated here, y equal to x to the power of x. What is the next step you take? The next step is that you would take the log of both sides, natural log of both sides. Take ln of both sides. Taking the ln of both sides, we're going to have ln y equal to ln x to the power of x. The ln used here is same thing as the logarithm to base e. It's a natural log. Natural log is always to base e. So don't get that twisted with the log to any other base. ln is the natural log to base e. So we've taken the ln of both sides and we have this. Now you will notice on the right hand side, we can apply the law of logarithm. Remember the law of logarithm, the power law of logarithm, which states that when we have the log of an expression raised to a certain power, that power comes behind to multiply the log. So we would have ln y equal to, this is the power, it comes behind here, that power comes behind here. So we're going to have x ln x. Is that taken? X ln x. Now the next step says differentiate both sides. Differentiating both sides of my equation, I'm going to have the left hand side is an implicit differentiation. Differentiating ln y, I'm going to have 1 over y dy dx. ln y, differentiating it, we have this 1 over y, then always add dy dx, equal to what you have on the right hand side is a product rule. Product rule states that u dv plus v du. This becomes our u. I will hold it, x. Now, differentiate ln x. If you differentiate ln x, we're going to have 1 over x plus v du. What's our v? Ln x. Ln x times differentiating x here gives us 1. So this becomes the left hand side we have the left hand side 1 over y dy dx equal to x cancels x. We're left with 1 here plus ln x times 1 we have ln x. All right. The next step now says multiply both sides by y. If you multiply both sides by y, we're going to have y into 1 over y dy dx equal to y into 1 plus ln x. So that is y cancels this y. I am left with dy dx equal to y 1 plus ln x. Then the final step, take back y to what it was. Y initially was defined to be x raised to the power of x. Therefore, dy dx will be equal to x raised to the power of x into 1 plus ln x. And this is the answer to this function x raised to the power of x. I'll be solving the other examples in the next video.